Okay, so this is the lecture number 12, and today's the session is about the another serial communication, which is known as the integrated circuit. Also, some people call it as I2C or TWI. So basically, since why it is called I2C is it has two-wire interface, clock and data. So you can have many devices communicating together to tight up this clock and data lines. So every microcontroller that you buy from Atmel or Microchip, big microcontrollers or any other ones, so they have the I2C communication hardware dedicated for that. So everything is handled by the hardware. So in this protocol, we have a master and many slave devices. The master could be typically the microcontroller, and the slaves could be any external sensor or device. Sometimes you can, if you have work on the LCD, you need plenty of wires, but you can have LCD screens, which has the I2C capability. So you just need to connect to two wires, and some sensors like temperature sensors and EEPROMs. Memory cards and everything can be communicated with your microcontroller using the I2C line. So although it is a two-wire interface, you need to have the plus VDD and common ground for all the devices. The ground should be tied up to everyone common. And this two line should be pulled up with the pull-up resistors, so which means like they are typically at logic high state. They are not, you should not keep them floating, so you have to tie them up to the VDD rail, so they are always at the logic high state. So if it is a 5-volt system, this could be 5 volt, and if it is 3.3 or lower than that, so that will be the corresponding voltage. And this pull-up resistors, the value should be carefully taken based on the distance of the of your line. If you are communicating with the long distances, you need to have different values. If it is a short distance, this R could be changed, and also R could be selected depending on the speed that you want to communicate with these devices. So if you buy any I2C incapable sensor, so in the datasheet, it is recommended the values of the resistance that you have to use, so you don't need to worry about that, and the maximum distance that you can connect to your device. So we will in detail discuss more of the sensors in upcoming lectures. But today I'm going to give you a brief introduction, what is this protocol and how it works. So I2C is chip-to-chip synchronous communication protocol. Synchronous means you always have a clock source, so rising edge, falling edge, or on the logic high or logic low state, only the data will be read or write. And it has several other names, but all refers to the same communication protocol. So integrated circuit is a common name, and some people prefer to call it as two-wire interface or TWI, and some people call it I2C or IC. So if you heard any of these names, so it is also always refers to I2C. So common devices that you can buy from the market which has the I2C capabilities, EEPROMs, LCDs, thermal sensors, real-time plugs. So it is easy to connect your microcontroller using only two wires. So these two wires are serial data, so the data will be transferred from this line, and the clock source will be in the other one. So you can achieve the speed of communication between 100 bits per second or 400 kilobits per second. And the number of slave and master devices, like you always have a one master, and you can have many slaves all together. Master plus slaves could be 128 devices if you're using 7-bit addresses. If you're using 10-bit addresses, you can achieve 1024 devices communication using the same line, right? So in order to make communication, in order to understand, so these slave devices and the master devices should have a unique address, right? So whenever they call this address, only this corresponding device will be respond and communicating. So this is how you interface your devices. This is I2C bus. It has this serial data line and serial clock line. And you have to pull up these two lines with the pull-up resistors. And so these could be any, first you need to have a master. So that is connected to the line and it has a unique address. You can assign the address by yourself. If you buy devices from the market, they have a dedicated address written to them, right? So you can't sometimes change them. So you have to accept that device has a unique address. Sometimes you can have another master, but that is not typically recommended. At one time, you can only have a single master of the system. You can have many more slaves. Otherwise, the system might be a little bit complicated. Still, you can handle it, but in typical application, you have single master and many slaves. And so the following communications methods are possible. So first one is the master transmit, which means your master one. Just forget this one, right? So we have only single master. So master can write values to the slave devices, right? So you can write any value to these devices. Let's say, like, if you have LCD screen, you can write whatever the character that you want to write to your slave device, which is connected to the LCD, the I2C bus. And the other one is master receive. For example, like this could be a sensor. So if the master wants to read the data from the sensor, so that is called a master receive. So it is requesting data to be sent from the sensor to the master, right? That is master receive. And so that is master reads the data from I2C slave. The other way is slave transmit. So which means like slave has the possibility of writing values to the master. Final one is slave can receive data from the master, right? Slave can request data from the master. Please give me some data. So that is called as slave receive. And sometimes if slave want to, like if a data packet is sampled and ready, so the slave can transmit that data to the slave. Slave can transmit data back to the master. That is called as slave transmit. So those are the 4 ways of communicating between this master and the slave. So this is a very basic video taken from YouTube. So that will be help you to understand little insight about how this system works.
I2C communication bus is very popular and broadly used by many electronic devices because it can be easily implemented in many electronic designs which require communication between a master and multiple slave devices or even multiple master devices. This implementation comes with the fact that only 2 wires are required for communication between up to almost 128 devices when using 7 bits addressing and up to almost 124 devices when using 10 bits addressing. How is that possible? Well, each device has a preset ID or a unique device address, so the master can choose with which device will be communicating. The two wires or lines are called serial clock or SCL and serial data or SDA. The SCL line is the clock signal which synchronizes the data transfer between the devices on the I2C bus and is generated by the master device. The other line is the SDA line which carries the data. The two lines are open drain, which means that the pull-up resistors needs to be attached to them so that the lines are high because the devices on the I2 bus are active low. Commonly used values for the resistors are from 2K for higher speeds at about 400 kilobits per second up to 10K for lower speeds at about 100 kilobits per second. Okay, now let's see the data protocol of the I2C bus. The data signal is transferred in sequences of 8 bits. So after a special start condition occurs, comes the first 8-bit sequence, which indicates the address of the slave to which the data is being sent. After each 8-bit sequence follows a bit called acknowledge. After the first acknowledge bit, in most cases, comes another addressing sequence, but this time for the internal registers of the slave device. After the addressing sequences follows the data sequences as many until the data is completely sent, and it ends with the special stop condition. Okay, let's take even closer look at these events. The start condition occurs when the data line drops low while the clock line is still high. After this, the clock starts and each data bit is transferred during each clock pulse. The device addressing sequence starts with the most significant bit first and ends with the least significant bit, and it's actually composed of 7 bits because the 8th bit is used for indicating whether the master will write to the slave, logic low, or read from it, logic high. The next bit, acknowledged, is used by the slave device to indicate whether it has successfully received the previous sequence of bits. So at this time, the master device hands the control of the SDA line over to the slave device. And if the slave device has successfully received the previous sequence, it will pull the SDA line down to the condition called acknowledge. If the slave does not pull the SDA line down, the condition is called not acknowledged and means that it didn't successfully receive the previous sequence, which can be caused by several reasons. For example, the slave might be busy, might not understand the received data or command, cannot receive any more data, and so on. In such a case, the master device decides how it will proceed. Next is the internal registers addressing. The internal registers are locations in the slave's memory containing various information or data. For example, the ADX345 accelerometer has a unique device address and additional internal registers addresses for the X, Y, and Z axis. So if we want to read the data of the X axis, first, we need to send the device address and then the particular internal register address for the X-axis. These addresses can be found from the datasheet of the sensor. After the addressing, the data transfer sequences begin either from the master or the slave, depending on the selected mode at the read-write bit. After the data is completely sent, the transfer will end with a stop condition, which occurs when the SDL line goes from low to high, while the SCL line is high. That's how the I2C communication protocol works.
Okay, as this guy talked about, like you have understanding about like how this data packet is sent. For example, now he told like there's an accelerometer which has an address of 53. So which means like so first step you need to do is write that slave address, right? So the master, if you a microcontroller like MCU, is your master. You have to generate this start bit and then write this 53 on the as the next 7 bits, right? Up to here, that should be written 53. So which means you are talking to your accelerometer, which is connected with the I2C bus. And if you like, accelerometer has 3 axes, X, Y, and Z. So X-axis reading is on this chip, like this is your accelerometer. So it has X, Y, and Z reading. So X register is stored in a address called 032. These addresses are different from the this device address, right? Device has a unique address which is known as 53. But internally, it has different addresses for their registers. So to where this data stored, right? So let's say like you want to read the X-axis data. In that case, you have to from this accelerometer, which is has the address of 53. So use you just start and write 53 on the as the slave address. And if you want to read is always 1. So logic you keep high. And if this slave device understand this data packet and this what is 7, and so that will pull this line down, right? Pull this like which means that master will release the line. So the slave will pull it down again, telling the master, okay, I have got your message. So I am the guy who is on this bus having a 53 address. So I am ready to communicate with you. Then you have to, if you want to read this X register in the accelerometer, so you have to tell this sensor, this is where I want your data. So you again you have to write 8 bits of this address, that is in hexadecimal it is 32. So you write that address, and then sometimes if the then again acknowledgement signal will be generated. So the slave understand that okay, I have to prepare my X-axis reading. Then the slave will send whatever the data stored in this X register through the line back to the master. So sometimes the master can acknowledge or not acknowledge, and if the master is happy, and he can stop the communication line. So if you're having this kind of sensor, this is the way that you are going to send the data packet to read the sensor. But there are some dedicated libraries to handle this, so you always don't need to understanding about in detail what is going inside the line. If you use Arduino or some kind of similar higher language interfaces, so there are some I2C libraries. So all you need to tell is the slave address, right? One single line on the slave address, and start the communication slave address and the register address, and the you will just receive the data. So you don't need to deal about these complicated things. But the microcontroller, if you use Atmega or any series microcontroller, it has a dedicated hardware. So if you write to particular registers, so it will handle this thing. But like Arduino, there are some dedicated libraries. If you use, it will do the same job that what you're doing in that studio. It will simplify and send it to the hardware to deal with this. So either way is possible, but today I'm going to give you some examples using Arduino, because dealing with at Bell Studio, this kind of things, it will take some, I think, at least 3 lectures to cover on this topic. But when I give you the theory, so you will understand, and later you can work on your own projects, you know what to do, and you can, by yourself, you can figure it out. Right. So this is the message format that which I have, that video has just explained. First, the start condition, and you have the slave address, read and write command, and the acknowledgement by the slave, and 8-bit data. If you are just getting the data from the slave without having an address, you can have this. If you want to ask from a particular address, this could be the address of the internal address of the slave. Otherwise, this could be data coming from the slave. And finally, we have this stop condition. And this is the same thing that we have just explained. Remember, like the most significant bit comes first when it is communicating. So that is slightly different from the serial communication that we have discussed in the last lecture. And this is the start stop conditions. So the start conditions happens when this clock line set high and the data line, the master pull the data line down. And then you can start the master will start the clock pulses. So depending on the positive half cycle of the clock pulse, so either this data could be high or low, and it will read like at this within this period. It will read if it is high, it will read it as 1. If it is low, it will read it as 0. And the stop condition is while keeping the clock line high, the master release the line, right? And data acknowledgement. So that means both parties will understand a successful communication has happened. So all you need to do is after sending a data packet, the slave will pull the line down. So if the slave does not pull the line down, which means there's some cause has happened in the communication, which might be like the slave might be busy with some other work, or slave is not ready to transmit or receive data. So the master has to handle this kind of situation. So if acknowledgement data bit is not received, you know, like this communication hasn't happened, right? So in that case, you can try again. And this is the read and write format. So if you want to write a byte to the slave, so the first one is the start bit, and then the slave address plus the write bit, right? If you want to write data, that should be this has a 7-bit address, and the last bit is if it is write, it is 0. And the slave will acknowledge, okay, successfully received my address and the write command, and then it will the master will send the data which it wants to write, and the slave will acknowledge, and the master stops. If master wants to read the data from the slave, let's say like this time we are not accessing an internal register, but slave will just send whatever the data is ready to send. So master start and write the slave address and the read bit. Read bit should be 1 if you want to read, and the slave acknowledge, and slave will send the data to the master, and the master does not need to acknowledge here, and he can stop because he got the data. And if you want to access to a particular register, so that I have just explained, so slave address plus write bit if you want to write, and slave acknowledge it, and then you have to tell the slave this is the particular address I want to get the data from, and the slave acknowledge, and the sorry, this is the particular address I want to write your internal register. So the slave send okay, send me the data. So the master send the data, and the slave acknowledge, and it stops, which means like a master can update write to particular registers. Sometimes like it can do the settings on particular sensor. So in that case, it has to write to the slave addresses. If you want to read from a slave address, it will be the same, but this time the slave will send the data back to the master. So now we have a small example, which is communicating to Arduinos using I2C. In that case, I have used two Arduino boards. This is two Uno boards. So you have to provide like, if you connect a USB cable here, make sure you connect this, connect them together. Like this guy should always take another 5-volt supply from this guy, right? Connect this 5-volt supply to this guy, and the ground should be common for both devices. Then you can connect this. This is the SDA line, serial data, and this is serial clock. Not like the previous case in serial communication, you connect the TX to RX and RX to TX, but here you have to connect SDA directly to the SDA of the other device, and SCL to the SCL. And you have to pull these lines to high using pull-up resistors. Then connect these pull-up resistors to the, again, 5-volt supply of your Arduino board. Not the V-in, but it should not be V-in, it should be the 5-volt output from the Arduino board, right? So then you know, like these lines are at logically high. And this guy is, if you are not connected to USB, always you have to feed the power from this board to this board. So then the boards will be activated, and they having a unique same common ground, and they are ready to communicate. Okay, so this is the code for that. So I'm using the wire.h library from the Arduino. So more details can be found from this link. If you go to references of the Arduino, all details are available. So you have to include the wire.h header in the code and void setup. Now, here that what I'm going to do is, I just forgot to tell you, I'm going to use, this is going to connect to my computer. So I'm going to send few commands. So if I'm sending logic, like type capital H and send to this Arduino, so it will read this high, the letter H, and transmit it through the I2C channel to this Arduino board, and pin number 13 is connected to the LED. So the LED will be light up if H is sent. And if I type capital L and send from the serial port to this Arduino board, so it will send the L from the master. This guy is the master, and this guy is a slave. So it will send this slave L, this letter L to the slave, and this LED will be turned off, right? So now I'm using the both serial communication and I2C. I2C is used to communicate between these two Arduinos. And in order to send few commands, I'm using my computer, which is using the USB port and serial communication. So this code is not written by me, like it is a very simple one available on the internet. So I just use it in order to you to explain how to get some idea. So since I'm using my serial communication, like with our I2C, so with the computer, so I'm using serial communication. So serial.begin, and this is the power grid, and I'm just printing a serial print command. Like this is I2C simulation example, just to make sure like my serial command is window is working properly. And then now I'm going to start my I2C communication. So I'm using wire.begin, which is the initialization of the wire library. So it will do the initial settings. This is the setup function. And now we are going to the loop function. So this is the serial available is the way that I read the command from my computer, right? If I type capital H and if I type capital L. So whatever the character typed on my computer and sent to here, so it will be read and is stored into a car variable, which is C. So serial dot read. So that will copy that capital H letter or capital L comes from the computer, and I will just send that whatever I have written there to echo it back and display on the computer. So I have successfully received that data. And if capital H is received, I'm comparing this variable with capital H. So I'm going to start the transmissions using I2C. And so that is the command wire.begin transmission. So more details can be found from this link. And this is my slave address. Sorry, this is my master address and the slave address, right? So both should be the same address. This should be the slave address. So I am calling to the slave number 5, which has the address of 5. And since I have received capital H, so I am writing capital H using wire.write capital H, and then I end transmission. So which means I have successfully sent capital H to the address of 5. So if there's a slave in the I2C bus which having a slave address of 5, it will receive this capital H. So if I type capital L from my computer and send it there, so capital L is received from the serial port. So I will again start communication I2C with the slave address of 5 and write capital L and then transmission. So this is the basically a master code, so which you have to upload to this guy. So then this guy is ready, and then you have to work on the slave code. This is that slave code. Again, now I don't need any serial communication because I'm just receiving and sending the data. So I have to include the wire.h, no serial port, and wire.begin with initialization of address of 5. So the slave need to assign his unique address, which is address 5. And then I have to call the event, right? So wire.onReceive event. Receive event is the name of the event. So it is some kind of function, right? This is the name of the function. Since that this LED that I'm going to control in this board, so I'm setting this pin as to output, and initially I will turn off the LED, right? So the initial LED is turned off. Then it comes to the loop function. So the loop function does not do anything, right? So it is just empty function. So it will loop in here without doing anything. And this event function is something like a interrupt, right? When it receive any data, so it will call this function and execute this and return back to the loop. So for example, now if this master sent this data wire.begin transmission to address 5 and write.h, so the slave know, okay, incoming messages, so it will jump to this event, right? It's something like interrupt, and then wait, go into this while loop and wire.available, which means if there's some data on the I2C bus to the slave, and read that data and copy to this variable C. And if that variable is capital H, turn on the LED. If that variable is capital L, turn off the LED. So this is a very simple code that you can try. even the Proteus has this Arduino library. You have to just it does not come default with the Proteus, but you have to download and copy into your library file. Then you can use the Arduino library in your Proteus. Then you can write this code in Arduino IDE and compile. And the hex file will be generated not on the same folder that you save your C file, right? It is saved on your computer temporary folder. So you have to go to your C drive and user, and then you have to go to app data, and then there's a temporary folder. So this is even if you use Windows 8 or 10, there's a temporary folder in the C drive. So there will be some like a Arduino or something like if you compile your code at, let's say, like 10:45 a.m., you can just see like there's a folder at that time. If you go inside, there will be like a hex file with the name that you saved your Arduino. So copy that hex file and import to your because these folders that is in the temporary going to be changed over the time. So better to copy this hex file to and put on your desktop or something, and then re-import it to the Proteus, right? That's why I want to tell you, like when you compile, that the hex file will not be generated on the same folder. It is on the temporary folder of your C drive. So you have to import that hex file to this Arduino if you're using Proteus. Otherwise, you can just use two Arduino boards and connect one guy to the USB port and another guy connected with the 5-volt supply of this guy and common ground, and you can try to communicate between these two guys. So this is the Proteus, and if you have already installed the Arduino libraries in Proteus, you can import this Arduino boards. And so this is how I have pulled this two lines, SDA and SDL are connected together and pulled up using a 5-volt battery supply. And you don't need to command these two using a ground because simulation understand it is working on the same ground. And also you don't need to connect 5-volt supply, but in real life, if you connect it to Arduinos, make sure you connect ground of these two devices common, and the this guy should be powered up with the 5-volt supply from the master. And this battery doesn't need, if you use like a USB port, and you can use 5 volts internal supply, connect these two resistors. And this is how virtual port, which is like acting as my computer, like the Arduino IDE, where I can send my serial commands. And this is pin number 13, which is connected to the LED. And I'm using an oscilloscope for demonstration purposes to show you how this signals works. And I have imported this master code to this guy and the hex code to this guy, which is compiled using Arduino IDE. And when I run this on, so you can see in the virtual terminal, I have just typed this in order to see if it works properly. Make sure you connect RxD to DXD and DXD to RxD. The virtual terminal can be imported from here. This is the virtual terminal. It is from this virtual instruments mode, and the oscilloscope is also there. Okay, right. Then I can now type capital H. So now you can see initially this pin number 13 is off. When I type capital H, you can see like 13 is on. So if I type capital L, so the LED will be turned off because the communication is done via this I2C bus. So in order to visualize this data, so you can see this oscilloscope. So now I'm on this oscilloscope mode. So I will type H. You can see now there's a data packet, right? Send using that. This is the clock, and this is the yellow is the clock, right? CL is connected to the channel A. Channel A is from yellow, and channel B is connected to the SDA data, right? So you can see this is a clock pulses, and this is the data, and how this start bit happens, right? When the clock is high and the master pull the line down, and likewise this could be simulated. I can try it again. So if you can capture this one, so you can understand how this works, right? Start bit and stop bit, and how this is the address, and 1 2 3 4 5 6 7 and 7 up to this is the address, right? So you have to use some kind of like a binary to decimal conversion table and see like this bit is 0, because here this is 0. You can think about this SDA line, right? This is 0 again, there's no data, 0 0, and here this 1 again, here it is 0, and here it is 1, and here again 0. So this is the address which is corresponding to, you can see like 0 1 2 3, and this is 5, right? If I'm correctly, this doesn't need to be there. So this is the address which is 5, right? 101, and up to this point, this is your address, and then we have this read write command. So writing is 0 always. Yeah. So likewise, you can then this again send in the data and like that. So you can debug using the oscilloscope if the data packets are sent or not. So the same thing is applied if you're working in real life. You can hook up an oscilloscope, and if your system does not work, this is how you're going to debug. And you can have you can use a virtual terminal, but it is hard to realize what is inside going on this I2C bus. If you know the protocol, and if you know the start, stop bits and addressing and everything, using oscilloscope and set it to these two lines, and you can visualize what is going on there, right? So if the address is correct and the slave acknowledged and like that, you can figure it out where this problem happens. So that is what you have to do in real life. So that is how you debug any system if it doesn't work, right? Otherwise you don't know where to start. If you have a oscilloscope, you can check that the addresses what you've written from here and goes in the line, and if the line has some kind of like oscillations and everything, there could be some troubles or electromagnetic interfaces. The data will not be transferred. Everything can be seen using this oscilloscope. I'm talking about the real life. And
sometimes you have to adjust these resistors in order to achieve the commands if there are some issues in these two lines. And if the slave does not acknowledge, you can also see from these data lines, and then you know like where the problem happens, and it is easy to use to troubleshoot. So this is how you troubleshoot. That is some kind of extra knowledge that I have given to you. So that concludes this lecture, and hope you have understand what is I2C, and I encourage you to go and read the I2C libraries and everything in the website. They have references and they have more example course, and in the YouTube also there are plenty of tutorials available regarding I2C. And this is a simple example that you can try by yourself. And other than that, if you're using, you can use any other sensors which has I2C capability or LCD screens using the Arduino inbuilt libraries to make any communication.